So, welcome to this particular module. In this module, we will see how we can measure the value of unknown resistance of a cable by a constant current drive using operational amplifier. So, let us see what exactly we mean by such a long title, right. So, when you look at the slide, what you see here, and I think this particular portion is not too much visible, but I will just try to redraw it if required. Let us see first aim. Okay. The aim of the experiment is to design and build a constant current drive using operational amplifier in its application as an unknown resistance measurement on breadboard. So, this particular resistance R3 which is shown here, right, we need to measure what's the current flowing through the resistance R3, and if you want to know that, we need to have either a constant voltage source or we need to have a constant current source. But if you see here, if we do not have that, then how can we design such a circuit which will give you a constant current or constant voltage source, so that we know the value of current flowing through R3. And to do that, we are using operational amplifier. The one correction here is this is the inverting and this is non inverting terminal. So, here we are using Zener diode, we are using a resistor R1 and we have a voltage source V which is 10 volts. Now, if you see here, the Zener we are taking off 2.5 volts, that means the drop across the Zener will be 2.5, and here what you will get is about 7.5 volts constant, right. So, this 7.5 volts we are giving to a non inverting terminal of the operational amplifier. That means because of the concept of virtual ground, if the non inverting terminal is at 7.5 volts, that means the inverting terminal also would have 7.5 volts. That means this 7.5 volts appears right over here, right. So, if you see, here is 10 volts, here is 7.5 volts, that means the voltage drop here is 2.5 volts, correct. Now, this 2.5 volts if we know, that means we know how much is the current flowing through the collector of Q2. If we know the current flowing through collector Q2, we can also calculate the current flowing through emitter, because it is related with the constant called alpha, right, and we can measure this value. So, thus if we know the current flowing through collector and emitter, we know what is the current flowing through the resistor R3. Now, this is the idea of this particular experiment, and if we just look at the read the paragraph, what it says that resistance measurement is an important electrical test in sensors to understand the change in physical parameter of sensor. Some examples include measurement of resistance in force sensing resistors when a force is applied, right. One of the application is when you apply force and we want to see the change in resistance, right, then you need to have a sensor which can show you the output in terms of change in resistance. Second example is thermistor. When you heat the sensor, the output will be in terms of change in resistance. Then another example is carbon microphones, right. So, which alter the resistance in response to changing acoustical pressure. So, there are a lot of examples where you see that resistance measurement will be a very important factor. Now, the magnitude of resistance, if you again see the slide, what is the last paragraph? The magnitude of resistance can be measured by different methods. One method to measure the voltage drop V across the resistance in a circuit and the current I through the resistance, right. This is one of the method which we can use, and the similar kind of concept we have used right over here in this circuit, and we will show you this thing in detail in terms of the experiments. The experiments, like I said, will be taken up by the TA, but let us see the procedure. The procedure is to assemble the circuit, the component and the materials as shown in the circuit. We need to connect the op amp, Zener diode, resistors, transistors and voltage source as shown in the circuit. The next one would be to connect a known value of resistor Rx. You can be R1, R2, R3 and ensure proper operation of circuit. So, Rx can be a known value of resistor. Then you can have connect a load or cable to find unknown resistance. This can be a unknown resistance that we want to measure. And finally, connect a long length of copper cable and short its ends, measure the resistance of connected copper cable. This is the idea of this particular experiment. Let us see in the experiment. We will continue this in terms of the experiment class. Let us see. I will call my TA to continue this particular session. If you have any questions, do feel free to ask me through the portal. Till then, take care. I will continue the class in terms of experiment.
Now, we will see how to use operational amplifiers in order to find out unknown resistance. We know that in most of the cases, generally in case of even sensors, right, most of the simplest way of designing a sensor is resistive type. So, and by measuring the resistance, we also we will be understanding the physical parameter. So, that means we should have to have a circuit in order to measure the resistance value. As we have also seen in the theory session, what are the different ways of measuring a resistance, and as we already seen in another different ways of measuring a resistance, we are now going to show you implementation of this particular circuit in multisim as well as on the breadboard. And before implementing it, we will understand how exactly the circuit is going to work in order to measure the unknown resistance. Now, if you recall, the simplest way of measuring any resistance is by applying some known amount of voltage to a system, or by applying some constant current as an input to the system and measuring the voltage drop across the resistor. As a result, since I know the current as well as the voltage drop across the resistor, right. So, suppose if this is my resistor, if I am applying some known current, that should be a constant current, some I, and if I measure the voltage drop across this V. So, if I want to find out R, based on the Ohm's law, we can say V by I is nothing but I, R. So, if I know this parameter as well as this parameter, this is easy to find out, but the problem is that getting a constant current source is of really difficult, and even providing a constant voltage source is also really difficult, and those are expensive too. So, any fluctuation in the voltages or any fluctuations in the current from the current sources, it results in change in resistance value. As a result, the accuracy of the resistance measurement entirely depends upon I value. So, in order to avoid these problems, we have also seen, we know that other ways of doing it by using Wheaton's bridge circuit or voltage divider circuit, but basically, right, those are other ways of doing it. Now, I am going to show you how to make use of operational amplifiers, right. As a result, by making use of the operational amplifiers with transistors, how can we measure a resistance, unknown resistance value. So, it is similar to that of the circuit that we have seen, that we are going to see in our temperature controller systems too, the plan that we have realized, but there was slightly different. Now, if we recall, if we understand, if we look into this particular circuit, right, in this case the purpose of the op amp here as well as transistor, right, the transistor here is in order to provide a constant current to the unknown resistance. In this case, R3 I am considering as an unknown resistance, right. We can use any R2 resistance value, R1 resistance values too, but R3 is an unknown resistance. So, the only intention is we have to find out what is the unknown resistance here. Now, how to understand the circuit? Just to understand the circuit, we are just recalling what we have seen in the theory session. So, what we are doing, we are using a Zener diode, we are using one resistor here, and we are using an operational amplifier, and this is PNP based Darlington pair, right. This is PNP based Darlington pair, and this is another resistor. Now, what is the purpose of a Darlington pair? Generally, when we go with a Darlington pair, the total gain of the system will be higher, right. So, because the amplification factor will be multiple of this as well as this, right. As a result, the current gain will be higher. So, whenever we are going with a high current applications, we will always go with Darlington pair transistor. It is not compulsory that you only have to go with a Darlington pair, right. That entirely depends upon the requirement. In this case, if we are limiting to milliamps or 1 amp of current, we can go with a normal single Darlington pair based transistor, or even smaller, we can go with a normal basic general purpose transistors too. But when we are going with the high current applications, Darlington pair should be must, otherwise the transistor cannot withstand such a high current flowing through the circuit. Now, whatever the op amp, we will see what is the importance of the op amp, but before that, let us just have a look on what is the use of having a Zener diode here, and what is the purpose of having this R1 resistor, right. Now, if you recall the working of a Zener diode generally been worked in a reverse bias condition. Now, when we see the value, the cutoff value, they have mentioned it as 2.5. That means that in reality, if you observe, no matter what voltage that you apply as an input to the system, and moreover when you see this is completely in a reverse bias condition, right, the drop across the Z0 diode will be always 2.5 volts, right, the drop across is 2.5. Now, so that means if I see the drop across the Z0 diode is 2.5, good. Now, what will put the voltage across the positive terminal? Since the voltage across this positive terminal is connected to the R1 resistor and the input voltage we are applied is of 10 volts, as a result, so 10 minus 2.5, energy neither be created nor destroyed. So, 10 minus 2.5 is 7.5 volts will be across this R1 resistor, right. So, that means the voltage across the positive terminal is 7.5 volts, right. But why 1K resistor, why not some other value, why not 10 ohm, why not 1 ohm? The reason going with the higher resistance value is when we look into the data sheet of Zener diodes or any semiconductor based system, they will always provide you the information of high amount of current that it can withstand for, right, operating current. So, when we look into the Zener diode, this particular diode, we can see somewhere around 10 to 20 milliamps of current is the maximum current that can withstand. So, basically the resistor R1 here is a current limiter circuit to protect the Zener diode not to damage, and since it is connected, the current flowing through this will be completely limited. So, in this case the current will be somewhere around 7.5 divided by 1K. So, this will be the current flow across this, right. So, it will be in milliamps, right, it will be somewhere in milliamps of current. So, as a result, because of smaller amount of current, it cannot damage, it will not damage the Zener diode. Now, what is the use of op amp? The purpose of op amp here is to maintain the constant current across your R3 resistor. How? If I take a simple transistor, if I want to understand, if the transistor is in on condition, right, the voltage drop across entirely depends upon what is the voltage that you apply, right, and what is the resistor. And if the resistance value is higher, the voltage drop across this will also be higher, right. But in this case, since we have to understand what is the unknown resistance value, if I know the current flowing through the circuit and if I measure the voltage drop across this particular circuit, it is very easy to realize the resistance value. So, for that case we require to have a constant current, but as long as if you are going with this method, you cannot guarantee that the current flowing through this, and moreover that entirely depends upon the resistance. But in this case we require to know this particular resistance value, right. So, that is the reason, in order to maintain the constant current across the collector as well as the emitter of the transistors, we are using a negative feedback by using an op amp. So, as a result what happens, since if you recall your op amp golden rules, one important golden rule is that virtual ground concept. That means the difference between the positive and negative terminal should be always equal to 0, or the V plus is equal to V minus. And from the previous circuit we understood that the voltage drop across this is somewhere around 7.5. So, as a result, since it is 7.5 volts, what will be the voltage across this negative terminal? That will also be at 7.5 volts. So, this is also at 7.5 volts. Now, so since it is directly connected to here, that means the drop across this, if I want to calculate the drop across this particular value, it is nothing but 10 minus 7.5. So, that means it is 2.5 volts of drop, right. So, that means I know what is the voltage drop across my transistor, across my resistor, and I know the resistance value. So, is it easy to calculate the current flow? Yes, right. So, how do we calculate the current flow? So, as we know from the Ohm's law, I want to find out I, which is nothing but V by R, right. So, V is 2.5 and R is 1K. So, the total current flowing is 2.5 milliamps of current. So, this is 2.5 milliamps of current is flowing. This is at emitter, right. So, and you also know, since it is a BJT, right, we know the relation between IC and IE. So, this is nothing but my IE, and the relation between IC and IE is directly proportional, right. So, I can also say it is almost equal to IE, approximately equal to IE, right. If I want to calculate accurately, what we have to do is that we have to look into the data sheet, and that depends upon what type of transistor that we are using. Generally, it will be somewhere around 0.99 the gain alpha value. So, if I multiply with alpha, then we can easily find out IC value too, right. Now, since our intention was to find out IC, so I am considering IC is also almost equal to IE, so all equal to IE. So, if I know this value, and if I measure the voltage drop across this particular value, right. So, I will be knowing V out. So, I need to know R3. So, R3 is nothing but V out divided by this 2.5 milli. So, this gives me the resistance value of R3. So, the main use of op amp here is to maintain the constant current through the circuit. No matter what, the current flow in the complete circuit will be 2.5 milliamps. That entirely depends upon what is the resistor that we are using and what is the resistance that we are using here, as well as, sorry, not this resistance, basically it depends upon what is the Zener diode cutoff voltage as well as what is the power that we are applying it here. So, these are the important things one has to understand, right, in order to realize or understand about the working of this particular circuit. I hope this is clear. Now, we will see whatever we have calculated is theoretically we have calculated, we will compare the result with the simulation. So, since we have to compare the result with the simulation, what I will do is that I will go with, I will open multisim, right. So, if you recall the complete multisim, since we are seeing the multisim from long time, so I do not want to explain everything. If you want to understand, just look back to the introduction to multisim video that we have created. So, I am placing an op amp, right, and the positive should be down, if we recall what we have seen in our circuit, and we require PNP transistor because we are using PNP. So, we require a Darlington pair. So, I am using the Darlington pair configuration. So, we can see here. Now, when we see after constructing, right. So, what I will do is that I will put a probe here. So, this is 2.5 and the alpha value is somewhere around 0.99. So, let me run the circuit, right. We have constructed based upon what we have seen the circuit. So, here we can see that 10 is input, the drop across D1 is 2.5. So, that means since it is 2.5, 10 is input, the drop across R1 will be 7.5, we can easily see 7.5196 volts. Now, since it is in positive terminal, the negative terminal will also be at the same value 7.5195. Now, the input voltage is 10 volt. So, if I want to calculate the drop across R2 resistor, it is 10 minus 7.5. So, 10 minus 7.5 is somewhere around 2.5 volts, right. So, 2.5 volts is the voltage drop. Now, since it is 2.5, this is 1 K, it will be 2.5 milliamps. So, when we calculate the value 2.4805 milliamps, approximately 2.5 milliamps. Now, see, our intention was to find out this unknown resistance. Since we do not know how to calculate the unknown resistance, what we are doing is, we know the resistance, but I know this current value, I will be measuring the voltage drop across R3. So, if I look into the voltage here, it is showing somewhere around 24.6 millivolt, right. Now, if I look into the alpha value, it will be somewhere around 0.99, right. So, it is 2.485 into 0.99 when I do 2.455 approximately equal to 2.46 milliamps. It is a 0.99 value, right. That is why it is a 0.4. So, no matter what. So, this is my the voltage across the current flowing in collector, right. So, if you recall the relation between IC and IE, IC is always equal to alpha times of IE. So, as a result the current across your collector will be always smaller than the current flow across your emitter. So, because of that, even though it is flowing 2.48 2.5 milliamps, it will be smaller than the emitter current, it is somewhere around 2.46 milli. So, now what is the voltage drop? 24.6. So, 24.6 milli divided by 2.455 milliamps. So, that means somewhere around 10 ohms. So, see, observe, what is the resistance? 10 ohm. So, forget about 10. So, what I will do is that I will go with somewhere around 100 ohms. Now, I do not look into the current, I only require the voltage. So, voltage is 246 milli. Now, we know that the current flow is 2.4805 milli, that is the current flow, current in your emitter, into 0.99, that will be the current 2.4805 into 0.99. So, which is 2.455 is the current flowing through the emitter, collector, alpha times of IE, and the voltage drop across is 246 milli. So, 246 divided by answer are 2.455, which is 100.2. So, observe here the resistance value that we have connected is 100 ohms. So, go with other resistance values too. So, I will go with somewhere around 500. Now, so 2.455 and this is 1.23 divided by 2.455. So, which is 501.5. So, this is volts and this is milli. So, 0.5 kilo, 0.5 kilo, right, that is nothing but 500 ohms. So, almost equal to, the value is almost equal to 500 ohms. So, this is a way. So, by using an operational amplifier, we can provide a constant current to our resistor, and by finding the drop across voltage drop across the resistance, since we know the voltage, since that is a constant current, it is easy to identify the unknown resistance, right. So, we will see whether it is working in the same way in our circuit too, in the experimental model. So, in an experiment we will connect everything in a breadboard, we will use LM336. So, LM336 is a Zener diode with a reference value of 2.5 volts, right. So, either we can go with a 10 volts or 15 volts. If we go with a 15 volts, the voltages will be little different, right. Now, we will see the experiment on this. So, actually in the experiment we have chosen LM336 of 5 volts. So, when we are solving, we have considered the Zener diode voltage as 2.5, but for the experiment purpose, just to understand about the next value, we have chosen the diode voltage, reference voltage as 5 volts. So, if it is a 5 volts, let us consider what will be the current flow and everything. So, since it is a 5 volts, the voltage drop across this will be 5 volts, and now the input voltage connected is 10 volts, and since complete 5 volts is dropping here, the voltage across R1 resistor will also be at 5 volts. Since, as you know, important property, golden rules of an operational amplifier, if the positive terminal is at 5 volts because of the virtual concept, the negative voltage will also be at 5 volts. Since this particular terminal is connected to at this point and the another end of the resistor is connected to 10 volts, the drop across the resistor will be 5 volts, isn't it. So, because the drop across the resistor is 5 volts, since we know the resistance value, we can calculate the current flow through this. So, as we know, according to the Ohm's law, I is equal to V by R. So, the voltage drop across resistor is of 5 volts, because this is 10, this is 5, 10 minus 5 will be 5 volts, and the current and the resistance that we are using is 1 kilo ohm resistance. So, 5 by 1 will be 0.5 milliamps. So, the current flow will be 0.5 milliamps. Okay. So, the drop is 5 volts and the current is 0.5 sorry 5 milliamps, right, 5 milliamps. This is also 5 milliamps because 5 by 1 k, right. So, since 5 milliamps and then since this is a Darlington pair configuration, the current flowing through this particular resistor will also be 5 milli, approximately equal to 5 milli, right. So, since our intention was to find out unknown resistance value, if I can measure the resistance across this, if I can measure the voltage across this R3 resistance, and by looking into the voltage and the current, right. So, voltage and the current will give us the resistance value, right. So, if I look into the board, look into the experiment board, here we can see this is an unknown resistance that we are considering. Since it is an unknown resistance value, by looking into the voltage drop across this resistor, this is a resistor by the way, and by looking into the current flow through the 1 kilo ohm resistor here, current flow through this resistance, we can understand the resistance value. So, since to compare the theoretical as well as with the actual resistance value, we have chosen we will be choosing as well as right now we have chosen 10 ohms resistance, right. We will see the calculations, and this is an PNP Darlington pair configuration, we have done it, whereas this is LM336. If you closely look into this particular value, it shows that 5 volts. So, when you see the input voltage applied to the power supply, which is of 10 volts, here we can see the input voltage applied is of 10 volts. When I see the voltage drop across the resistor, so because this particular Zener diode has onboard connected with a resistor internally, it has resistance as well as Zener diode configured together. So, when I look the drop the voltage that we have connected at third terminal, which is nothing the positive input of operational amplifier, it shows 5 volts. The reason is that the Zener diode whatever we consider is a 5 volts, and internally it has a 1 kilo ohm resistance, and since we are measuring across the resistance value and power supply is at 10 volts, it will be 5 volts, 4.97 closely 5 volts. Now, what about for the negative terminal? It is also at the same voltage. The reason is that virtual ground concept. Now, what will be the voltage drop across the resistance? Input is 10 volts connected, and other end of the resistance is also 5 volts, 10 minus 5 closely 4.95, which is also 5 volts. Now, we know it is a 1 kilo resistance, and the drop across the resistor is of 5 volts. It is easy, the current flowing is of 5 milliamps, that is clear. Now, let us find out the drop across resistance. So, this is our resistance. So, I am checking the voltage drop across the resistance here and here. How much it is showing? 57 millivolts, right. So, when we calculate, so we got, so we need to calculate R3 resistance value, we got it as 57 millivolt, and the current flow is up roughly 5 milliamp, by 5, right. So, when we calculate it is of 11.4 ohms, right. The value is almost close to 10 ohms. The difference is because one thing is whatever the resistance value is very smaller, that is one thing, and the voltage that we got is not 5 volts, 4.96. So, when we calculate 1 by, so all put together and the current flow through the collector, right, will be always at smaller when compared to the emitter value, but we have roughly considered as a 5 milliamps. So, all put together we got an the precision of we got a difference of 1.4 ohms. and moreover we cannot say it is 1.4 ohms difference too. The reason is that the resistance will also have some tolerances, right. We will take another resistance value. So, right now I have a different other resistance here, if you observe. So, this is one more resistance, the resistance value is 25 ohms, here we can see, and 25 ohms, and this is of 10 watt 50 watt resistance, whereas this is 50 ohm and 50 watt resistance. So, what I will do is that I will connect this resistance resistor once. Let me switch it off. I will remove this. The current will not change. What will change is the voltage drop across resistor. The reason is that the resistance at that particular terminal is already fixed, and since we are forcing to have a drop across the resistor is of 5 volts and the resistance is of 1 kilo ohms, it will be always at 5 milliamps no matter what. So, everything same, nothing I am changing. Once again I will check the voltage across positive terminal 4.98 and negative terminal again 5 volts 4.98, voltage drop across 1 kilo ohm resistance, right, same. Now, when I check drop across resistance, how much it is showing? 246 millivolts. Now, if I calculate here, it shows 246 milli right divided by 5 milliamps. So, what is the value? 246 divided by 5, 49.2. So, the value is, so what is the resistance that we have connected? When I look into the resistance, it is of 50 ohms. When I look into the resistance on the circuit, here if you see, it is of 50 ohms, right. So, the value whatever we got is also almost close to same. Now, I will change the resistance value from 50 ohms to 25 ohms. Let us see with the theoretical whether we get the same value or not. So, the resistance, the connected resistance in this case is of 25 ohms. Let me switch on the supply and I will take the multimeter probes. Let me connect the voltage across this resistance. It shows 124 millivolts, right, 124 millivolts. So, when I calculate the value, it is exactly half of the previous one, 124 milli divided by 5 milli. So, this is nothing but 124 divided by 5, 24.8 ohms. So, the connected is also 25 ohms and whatever we got is also 24.8, which is almost close to that of what we have connected. So, by using such kind of a driving circuits, by using such kind of a systems, even we can even find out unknown resistance value. The only thing is that it is forcing to have the current flowing through the system to be of always a constant. That is because of your negative feedback connected to your operational amplifier, and because of your G0 diode connecting in a reverse biaser condition, you can fix your reference value. As a result, the current flowing will always be fixed, and the speciality of LM336 is that you can even adjust your reference values too, right. I hope this complete experiment is clear to you. Thank you.